All right, so we worked on the same problem. I'll walk you through it a little bit more thoroughly. So the goal here is they actually want to compare the brains of dinosaurs to the brains of birds. And they don't want to spend a lot of time pulling out the brain volumes. They'd rather think about how the structures of the two brains are functionally different. But right now, they're spending a lot of their time picking through and selecting out those brain volumes. So it's a lot of wasted effort. So here's the process today. They take the skulls, put them through a CT scanner, spits out a ton of skull slices as TIFF files. Then it has to go through this expensive proprietary software that we've already spoken about. They have to manually select out the area from each of those flat files. It gets compiled together into a 3D rendering, an STL file. Then it has to be smoothed, and then they get to do the real important stuff, the stuff that they actually studied for. So these are the main pain points. It's heavily manual, very burdensome. They have this extra smoothing process that's required, and the brain volumes that they're getting out of it are still kind of coarse.
So like we said, we'd like to make this entire process of taking these CT scans of skulls and identifying important parts of them completely automatic. We want to take out as much effort from the paleontologist as possible so they can go through an entire database of tons and tons of these scans that you've seen this afternoon. So what we tried to do is we had a couple of parts. So the first part of this is doing this automatic process. So we wanted to automatically identify an outline of the skull, and then we wanted to automatically identify important parts of that outline. These are two visualizations of a bird's skull. So you see it's actually turned on its side. So at the top there's like an eye hole, and down here is the beak. And so we've identified just the outline, just the important information that kind of summarizes this skull. And then we'd like to be able to we have an algorithm to do clustering for this, so to find parts of this parts of this outline that are important, and then in theory we could take these clusters and hand them to a paleontologist who could label them. We could say, okay, this is the brain case, this is maybe the beak, for instance. That clustering process takes way too long. So the code exists, Aki, if you're interested in using it, but it doesn't run in 24 hours. But it doesn't use any human interaction. You just sort of plug and chug, and then you just click like one time using some tools. And once you have all of these things, you can plug them into the tool that we also developed that we're going to talk about now.
Yeah, so like we said, we wanted to make it easy for paleontologists to compare different brains. So to do that, we used a tool, Blender. It's an existing open source tool that lets you play with some 3D models. So we wrote a Python script that runs with Blender that sort of stacks some 3D brains on top of each other and edits the transparency and color so you can kind of compare the brains. So yeah, on the right here is some dinosaurs, and then left some birds. So yeah, in the future, we would want to be able to write some code that kind of detects the different parts of the brain. We don't know anything about brains, so if you go back to that slide, I'm not even sure if that's like the right way up. So it would be really cool to have some code that could look and sort of define which lobes are which, so it's easier to compare them. So,
yeah, so just to summarize our future work, we're hoping to more thoroughly integrate the code with Blender, the open source software that we were using, and also make sure that the Blender tool can work with outputs from our 3D rendering tool in MATLAB. Thank you.
Sweet.